We are going to do lots more derivatives of functions moving forward in our next sections and our next chapters. There's going to be a lot of applications using derivatives. However, before we get too far ahead and doing the applications, I want to talk about a higher order derivative or higher order derivatives. So if we have a function, h of x equals 5x to the 6th, we can take the derivative of that function. Let's go ahead and take the derivative of this function, and then take the derivative of that function. Take the derivative of the resulting function. If we take the derivative, this is a basic power rule, so we can take 6 times 5 as the coefficient, and then x to the 5th. 5th is our exponent. So the derivative of h of x is 30x to the 5th. Now, just for the sake of argument, I'm going to say, if I called the derivative, I don't know, k of x, 30x to the 5th. So if I call it k, then I can take the derivative of the function I obtained. So I can take the derivative of k. That's like k prime of x. And again, this would be a power rule. So 30 times 5 would give me 150. X to the 5th, we reduce the exponent by 1, and you get x to the 4th. So the derivative of 30x to the 5th is 150 times x to the 4th. If I called that something, let's call that L of x. Well, I can take the derivative of L of x. The derivative using the power rule becomes 150 times 4, which is 600, x to the 3rd. And you could keep going on and on and on with this process. You could just keep taking derivatives and derivatives and derivatives. Now, what we're finding is called a higher order derivative. Notice that k prime was really just the derivative with respect to x of h prime. And the L of x was that. The L of x was simply the derivative. Let me write this down. Of a derivative of h prime of x. So it's basically the derivative of a derivative of a derivative, okay? And what we're getting at there is the concept of a higher order derivative. It's basically when I take the derivative of a derivative of a derivative of a derivative, and I keep going with that. Now, the notation we're going to be using, since we used f prime for the first time we took a derivative, we're going to use f prime prime or f double prime when we take a derivative of a derivative. Now, the first time we take a derivative, that's called the first derivative of x. If we take a derivative 2 times, that's called the second derivative of f of x. So as long as we can keep doing this, as long as our function is differentiable, we can keep doing this over and over and over. We can take a first derivative, we can take a second derivative. Second derivative is just f double prime. A third derivative would be a derivative of the second derivative. So f triple prime, or f prime prime prime. And then once you start doing this, after you get past 3, you say, well, that's just too many ticks to write. And so we do the nth derivative, f, and then we put this in parentheses. We want to make sure it's in parentheses so it doesn't look like an exponent. So f with an in parentheses in the exponent means the nth derivative of f. And the way you get that is you just take the n minus 1th derivative and then take the derivative of that thing. So you can keep going on as far as you'd like. That's what the idea of higher order derivatives are. So let's take a look at what we did. Well, we've done this already. The first derivative, h prime of x, was 30x to the 5th. The second derivative is h prime prime of x, which was 150x to the 4th. The third derivative, we found that. That's h, and then I do a triple prime of x equals 600x to the 3rd. That's what we found, so that's our notation. If you want to do a fourth derivative, at the time you get to a fourth derivative, instead of putting all of those prime marks in the exponent, you just write in parentheses a 4. You could technically write all those primes if you'd like, but what's that? 1800x squared. And the same thing for 5th. You would say h, and then in the exponent, you'd write a 5 in parentheses. Notice that we want to make sure that that's a 5 in parentheses, because if you don't write the parentheses, then it looks like you're taking it to the 5th power. If I just write a 5 there, that just means h to the 5th power, but with parentheses, it means h to the 5th derivative of h. So that's the different notation. And you could keep going on. You could take a 6th, 7th, and 8th, any derivative you want. You could keep going on and on and on and on. So that's the idea of higher order derivatives. You take a derivative, and then take a derivative of that function, and then take a derivative of that function, and so on and so forth. And we get this recursive system where we can take any order derivative we want, as long as it keeps existing. Once it doesn't exist anymore, then we can't go any further. But most of the time, the functions I give you, you can take as many derivatives as you could want. So here's what I'd like you to do. I'd like you to take f of x equals 9x squared and g of x equals natural log of x, and take the first 4 derivatives of those 2 functions. Push pause on the video, and on the next video, I'll explain how that works.